All right, let's dive right into one of the deepest, most fascinating mysteries in all of physics. Why does all the quantum weirdness just stop at our scale? We're going to explore two really compelling but completely different theories trying to answer that. One says gravity is the culprit, and the other points its finger at the very fabric of space, the vacuum itself.
So here's how we're going to break this down. First, we'll set the stage and really define the central mystery. Then we'll get to know our first contender, the idea that gravity is the one pulling the plug on quantum effects. After that, we'll meet the challenger, a newer theory that says the vacuum is responsible. We'll put them head to head, look at a real-world experiment that could decide the winner, and then wrap up by asking which one gives us a more complete picture of reality.
So this is the fundamental question, right? At the smallest scales, quantum mechanics is law. It says a particle can be in many places at once, in what's called a superposition. And we've proven this time and time again with electrons, atoms, even surprisingly large molecules. But you've never seen a coffee mug or your car or another person exist in two places at the same time. So why not? What is it that stops this incredible quantum behavior from scaling up to our everyday world? Well, that invisible line in the sand is what physicists call the quantum classical boundary. It's the transition point. And for the better part of a century, we've been arguing about where that line is and what's enforcing it. The two theories we're looking at today go a step further. They don't just guess where the line is, they propose a concrete physical reason for its existence. Okay, first up, we have the reigning champion. This is a very well-respected idea called the Diósi-Penrose model, or DP for short. It's got some serious heavy hitters behind it, and it offers a solution that is both elegant and pretty dramatic. The core idea of the DP model is refreshingly direct. It says that gravity itself is what actively destroys quantum states. In this picture, gravity isn't just some passive background stage for the universe. It's an active participant, a kind of cosmic police force that stamps out quantum weirdness. So how's it supposed to work? Well, according to DP, when an object is in superposition in two different places, it essentially creates two slightly different versions of spacetime. The model says that spacetime just can't tolerate this conflict. It creates a tension, an instability called gravitational self-energy. And when that energy difference gets to be too much, reality snaps back, forcing the object to pick one location, and poof, the superposition is gone, the wave function collapses. And why this matters is huge. It means gravity has a second job we never knew about, not just bending spacetime, but actively enforcing classical reality. And this is the real takeaway. The DP model isn't just an idea, it gives us a testable formula. That tau symbol, that's the collapse time, how long a quantum state can last. And what the formula tells us is that the collapse time is inversely related to that gravitational self-energy. Put simply, the bigger and more massive the object, the bigger the space-time conflict, and the faster gravity forces it to become classical.
All right, now let's turn to the challenger, the dynamic vacuum field theory, or DVFT. This theory takes a totally different approach. It says, forget gravity. The real issue is with the vacuum of space itself.
I really like this way of putting it. If DP's motto is gravity kills, then DVFT's is that the vacuum runs out of phase patience. It's not an abstract mathematical rule. It's the idea of a physical medium reaching its absolute breaking point. You see, DVFT doesn't see the vacuum as empty. It sees it as a physical thing, a dynamic medium. A good analogy is to think of it like a perfectly stretched sheet of spandex. Now, if a tiny particle is in superposition, it's like making two tiny little dimples in the sheet. No problem. But if a massive object tries to be in two places at once, it's like trying to push a bowling ball down in two different spots. The fabric just can't handle the strain. It tears. And in the same way, the vacuum's ability to maintain a coherent quantum state breaks down. It decoheres back into a normal, classical state.
Now, DVFT also has a predictive formula, and this is where it gets really interesting. You see that c to the fourth term? That's the speed of light, to the power of 4. It's a ridiculously huge number. What this means is that its effect is much gentler. It allows quantum states to persist for longer than you might think, leading to a much more gradual transition from quantum to classical, which is totally different from the sudden snap that the DP model predicts.
Okay, so we have two completely different stories unfolding. In one corner, gravity is the destroyer. In the other, the vacuum is this fragile medium that can only take so much. Let's put them side by side and really nail down where they differ.
This slide really gets to the core of it. What's the trigger? For DSP, it's an inherent instability in the geometry of spacetime itself, this concept of gravitational self-energy. But for DVFT, it's a physical stress, a phase mismatch within the actual medium of the vacuum. That's not just a subtle difference in wording, it's a fundamentally different kind of physics.
And this table just lays bare how deep these differences run. DP talks about a sudden all-or-nothing collapse of the mathematical wave function. It's like flipping a switch from on to off. DVFT, on the other hand, describes a gradual physical breakdown, a decoherence of the vacuum itself. It's more like a crystal-clear radio signal slowly fading into static. And the implications just keep stacking up. In the DP world, gravity is the star of the show. But in the DVFT world, the vacuum is the stage, the medium, and the final judge of what gets to be quantum and what doesn't.
Okay, so this is where it gets really exciting. These aren't just a couple of cool ideas to argue about. They make totally different predictions about the real world, predictions we can actually test. So how could we design an experiment to be the ultimate referee between them?
So let's imagine an experiment that might be possible in the near future. We take what's called a mesoscopic object. That's something in that gray area between the micro and macro worlds. Let's say it has a mass of about 1 billion atomic mass units, or 10 to the 9 AMU. And somehow, we manage to put this entire object into a superposition.
First question, what does our reigning champ, the DP model, predict is going to happen? Based on its formula, how long should that quantum state be able to survive before gravity shuts it down?
The answer is about 17 hours. Yeah, you heard me right. According to DP, at this mass, gravity's destructive influence is still pretty weak. The superposition should be stable for a long, long time, certainly long enough to measure in any lab experiment.
Okay, hold that number in your head, 17 hours. Now for the challenger. What does DVFT predict for the exact same object in the exact same experiment?
About 1 microsecond. 1 millionth of a second. I mean, let that sink in. This is a jaw-dropping difference. DVFT says that at this mass, the vacuum is already strained to its breaking point and can't maintain the quantum state. It should vanish almost instantly. 17 hours versus 1 microsecond. They're not even in the same universe.
And this is what makes for such a beautiful, clean experimental test. If we start seeing quantum effects gradually fade away for objects around 100 million AMU, that's a massive point for DVFT. But if we can push superposition all the way up to 10 billion AMU, and then it suddenly just vanishes, well, that would strongly favor DP. There's no ambiguity, no gray area. The source material is clear. Their predictions don't overlap. You run the experiment, and you get an answer.
This brings us to our last and maybe most profound point. This isn't just about which theory gets the numbers right. It's about which one gives us a deeper, more fundamental explanation for why there's a boundary in the first place.
And this quote really says it all. You could argue this is DVFT's strongest claim. The Diósi Penrose model essentially postulates that collapse happens. It's an extra rule added to the system to make it work. DVFT, on the other hand, claims to derive the boundary from the known physics of the vacuum. The transition isn't an extra rule, it's an emergent property, a failure mode of the underlying medium. It doesn't just say that it happens, it tries to explain why.
And so we end with this question. What if the answer to one of the oldest mysteries in physics isn't some abstract mathematical rule, but a tangible mechanical property of the most fundamental substance in the universe? It completely reframes the problem. The boundary between the quantum and classical worlds might not be just a line on a graph. It could be the literal breaking point of the vacuum itself. And that is a truly wild idea, one that future experiments are poised to finally put to the test.